everyone, and thank Christian for this event and opportunity. My name is Albert Tanker. I'm a graduate student which specializes in engineering biochars, actually. I'm from Middle Technical University, Turkey. I'm also a researcher in EU project, SysInc, with Christian, where we investigate several CDR technologies that includes biochar. And today I will briefly talk about one of our project deliverables, which focuses on integrating biochar and carbon capture and storage systems. Just so, as we all know, biochar is a very effective CDR technology with a high technology readiness level, and currently a lot of resources have been gathered for it to be one of the main CDR pathways in especially Europe. However, the production of biochar, mainly pyrolysis, itself is an emission source due to it's an energy-intensive process. I mean, you got to supply energy to pyrolysis, and if it's fossil source, it's bad for the environment. And another thing, the byproducts, the bio-oil and syngas, are also contain carbon and contain carbon dioxide. They can be burned, they can be fuels, but burning them to gain electricity or gain energy would only make them like carbon neutral, not carbon negative. So we can do better. We can make biochar more carbon negative. But how we can do this? There's an already established technology, carbon capture and storage. I mean, they're doing it in bioenergy and carbon capture storage plants. They're doing all over Europe. Several projects are underway. So what's carbon capture and storage? It's basically it's a process where you capture the carbon from flue gases from anything actually, and you compress it, inject it underground or any geological storage facilities such as saline aquifers or depleted oil and gas fields. And by incorporating CCS to our biochar production, we can still achieve energy generation from syngas or even bio-oil. The pyrolysis could become self-sufficient. If it's self-sufficient, it continues to be self-sufficient in terms of energy, of course. And the whole system, the whole pyrolysis or biochar production facility can improve its carbon footprint compared to standalone biochar production. And this would also increase the energy efficiency of the whole plant. So that established in this project, our aim is to integrate a CCS system to a biochar production plant to reduce CO2 emissions associated with pyrolysis while sustaining an efficient use of pyrolysis byproducts, syngas and bio-oil within the system. We're just not exporting it, we're not just selling it, we're using it within the system. And we do not want to compromise the performance of the CCS. It's like very efficient system, and we don't want to damage its CO2 reduction potential, actually. So in our methodology, there's actually one primary approach. It's just a system integration. We take systems for biochar production and as generic CCS system, and we merge them, but we merge them in a way that maximizes the efficient use of byproducts, while linking as many as possible energy and material flows within the system, within two systems. To do that, use very basic tools. We conduct our carbon, energy, and material balances in Excel with the help of macros and several add-ons. We then validate our results in thermodynamic simulations. DVSIM is a free tool, just like Aspen Plus. And for not life cycle analysis, but for we need some emission data from actually background emission data to calculate the CO2 removal potential of our system. So we use equipment databases and Singapore software. And for the plant layout and the economic modeling, actually we use IACM, Integrated Environmental Control Model. It's a free software too, from the University of Wyoming, I guess. As I said, this is an just a modeling, just modeling project. We didn't do any experiments. So most of our data has come from literature or just interviews with the experts that are in the biochar production plants or patents, reports, anything we can find, anything reliable we can find in the literature. There are several gaps in the literature. We try to fill them with simulations, with SimaPro, with databases or IACM simulations, basic balances, and yeah, basic equations for most of the time for the fluid handling equipment, power equations, etc., etc. And we also get our cost data from international organizations that publish the cost value for many of the things on an annual basis. And for our design basis, we think of a like very large industrial plant, like because we're thinking of integrating a biochar production plant into an existing power plant or existing base power plant. So we thought we can maybe produce 5 tons per hour of biochar in a 100 megawatt power plant. It's a big power plant, but with biomass fired power plant like Drax in UK. I guess it's like 650 megawatts. And also Sweden Exergi are doing bioenergy with carbon capture also. There's also, at least they're trying. And we assume that the plant could operate for 30 years, and after its end of life, it can also just the monitoring and verification part of the project for the assessing the permanence of the carbon dioxide capture. It could just go on for 7 years, totaling 100 years lifetime for whole project. We have chosen our biomass as Santos. More on that later. I will talk about why we chose this biomass, and we divided our system into 3 subsystems so we can analyze it like more efficiently. The biochar production unit, biomass energy production unit, and the CCS unit, basically. This is a very simple representation of our flow chart. I have divided this into 5 sections. First of all, biomass pre-processing. This process, the whole process actually starts with cultivation of biomass, and we transport that biomass to the facility, and it goes generic pre-processing steps, like we grind them and dry them to 2 millimeter particles and at around 5% moisture content because it will be fired in the boiler. And then we split it according to our requirements, like one part goes to biomass power plant and the other part goes to pyrolysis facility to produce 5 tons of our biochar and 100 megawatts of energy. And within the biochar production unit, the pyrolysis takes place in a continuous agar reactor at 500 degrees Celsius. The existing large biochar particles, we collect them in a container just beneath the jacket, just beneath the pyrolyzer. While the gases are proceeded to cyclone separator, so we can just separate the small biochar particles from the pyrolysis gases. And then all the biochar particles are collected and washed with water to stabilize it to 30% moisture content to better handle it actually and to cool it down to a little bit. Then it's loaded. Maybe it's again pelletized, or maybe it can just be sent to the soil amendment and the fields to apply. And the particle-free pyrolysis gas, we have them after the cyclone. We push them to a condenser, we separate them to bio-oil and gas as much as possible. And the majority of that syngas is we combust it with like 10% excess air in a burner located in a jacket of the pyrolyzer to sustain that 500 degrees Celsius temperature. Most of the biochar production plants do that. And the bio-oil and the remaining syngas, like 30% of the syngas remains. And we send them to the combustion unit to gain energy from them. The combustion is a threefold boiler within the biomass energy production unit. Dry biomass along with bio-oil and syngas are burned here together. Like we can, in the literature, it can be achieved like 89% heat efficiency, and we burn it with 1.1 XSA ratio. The energy contribution calculations said that 70% of the energy, boiler's energy, thermal energy output is from biomass itself, and 26% we get from bio oil, and 4% we get from syngas. The generic thermal heat, we then just converted the electricity via a simple turbine to get our target 100 megawatts of power. The efficiency of turbines we took as 33 or 34%. It's generic steam turbine. And we have exhaust gases from both the boiler and the jacket around the pyrolyzer, the burn from the burner. Then we combine them. If we have excess heat in them, we can just use that flue gases heat to plant operations. Can preheat the combustion air, etc., etc. And then we cool the flue gas. We send them to flue gas treatment unit, and then to the carbon capture unit, where we capture CO2. We absorb CO2 through a monoethylamine absorption stripping process. We can get 90% of efficiency in the literature. They say around 90%, 85% efficiency, and up to 99.8 pure CO2 stream we can get from at the condenser of the stripping column. The captured CO2 is then transported a piping stream and pumped into a geological reservoir from in the sea or in the depleted oil field, etc. And the flue gas is then emitted from the stack, along with that 10% uncaptured CO2. But I mean, you can't be 100% efficient in this in those kind of things. The energy for the CCS is a very energy-intensive process. The main energy input of that absorption stripping process comes from the boiler of the column. We can supply that energy. We are already producing a thermal energy here, and we can supply that energy by just drawing an intermediate pressure steam from the turbine, from inside of the turbine, and just feed that into a reboiler to make the CCS units energy to get CCS units energy demand. The mass energy and the carbon balance results demonstrate that this system can sequester approximately 1.34 megatons of CO2 per year through combined biochar and CCS process, as you can see in the figure. The majority of this comes from the 1.2 megaton of CO2 per year is due to CCS from the energy production, just CCS of the boiler flue gas. The CCS process from the biochar production unit contributes additional like 73,400 tons of CO2 per year, accounting around 5% of the total potential. And the biochar itself contributes 85,585 tons of CO2 per year, and that corresponds to around 6.4% of the total potential. And in total, we can achieve a carbon sequestration rate equivalent of 1.13 kilograms of CO2 per kilograms of biomass. That results in capturing approximately 69% of original carbon content in the biomass. The rest is gone to the atmosphere through that 10% loss and the losses from the stability of the biochar. However, this itself is not enough for assessing like the CO2 removal potential of any system. So we use another metric that's called climate effect value, or CEV. CEV is actually a very critical parameter for assessing the climate impact of CO2 emissions occurring at different points in time by that quantifies the temporal effect of emissions. Then it enables us to compare long-time effectiveness of various technologies. This metrics offers a more comprehensive way of understanding how various CDR approaches mitigate climate change or their lifespans, unlike any traditional metrics. Just they are non-temporal. It takes account that the biochar and geological storage (CCS) both present a risk of leakage not the risk, but they obviously leak, but at what percent they leak? That's a good question. Third, the life cycle. And also we took a very large amount of biomass and we kind of mostly burn it or turn it into biochar and burn the rest. So it is different than waiting the, the natural decay of biochar, because natural decay happens over the span of 100 years, and we take the biochar, we burn it instantly. So that have a different effect on climate. It's not just numbers, but how long CO2 stays in the atmosphere has an effect on the upcoming CO2 emissions. So this actually calculates that effect and gives us a factor between 0 and 1, meaning that if we just multiply our result 1.34 megatons of CO2 per year with that factor, we can get the temporal and the let's say climate effect value, actually real effect of our technology on the CO2 reduction. And we can say that the cases we have 3 cases here based versus average, because like everything, we cannot be sure about the exact leakage rates of biochar or exact stability of biochar or risk of leakage of geological storage units. So we have done 3 scenarios, best versus on average, based on this leakage rates or leakage profiles, you can say. In the average, after 1,000 years, in a 1,000-year time frame, we expect like 90%, let's say, efficiency in CO2 removal for our system. Another method for assessing CO2 removal potential is the net carbon removal benefit, which the EU Commission utilizes to evaluate different CDR projects. The traditional calculation method is here used by EU Commission and outlined in establishing a union of certification framework for carbon removals. It's an EU paper. That is the formula. It's a very basic and generic CO2 removal CO2 removal potential calculation method. In here, CR total represents the overall CO2 removed by the project over a specified time frame. This project achieves a 1.34 megaton per year. And the CR baseline is actually the carbon removal under the baseline. So it represents the standard practices or regulatory or market conditions that this activity takes place. Currently, no standard practice, law, or anything, any regulation exists for carbon dioxide removal. The focus on is more like reducing the CO2 emissions. So we just take is at 0. Most of CDR technologies do that. Greenhouse gas increase represents the CO2 emissions that occur over the project's lifetime due to project itself. This value includes emissions due to construction of the plant and the infrastructure needed for the operation. And also the main emission comes from the transportation of the biomass into the facility and the biochar to the fields. Also, we had to consider that 10% uncaptured carbon in the biomass as an emission. So when we add all them up, we get a total of 361 megatons CO2 over a project lifetime in emissions. And that results in 32.84 megatons of CO2 for base case, 31.63 and 32.35 for worst and average cases. That's megaton CO2 not per year, over a lifetime of the project. And that doesn't end here. Of course, everything is related to money, and everything need to be evaluated in terms of financial feasibility. So we just do a very quick, not very basic financial analysis. We use 2 metrics here. PPCV is the price for climate effect value, and ppCO2, that's the price per ton of CO2 removed. And the first one is actually the temporal version of the second. These are the formulas. We took them again in the literature. That is, here's the I is the investment cost, OM, operation and maintenance cost, MRV, monitoring, reporting, and verification, and etc. R and I are the discount and interest rates. We just take 0.10. That's a standard number for calculating this kind of stuff. And REV is for revenue. And to calculate that, the first thing we did with just model the representative plant in IACM. IACM is for just modeling actually coal power plants, but you can change the fuel properties. So we just change the fuel properties to biomass. And we use that model to calculate the investments and the operating costs. And then we incorporate biochar production in the pyrolysis facility to the investment cost and operational costs, along with the land cost for establishing the facility. And yeah, we will talk about the lands further down in the presentation. And the operating costs are, we actually modeled operating costs such that the model does not include any transport or purchase of the biomass. We took these values from the literature and added them on. And the annual MRV costs are assumed as 15% of the total cost, and then we divide that by the operation years. The labor requirements and for the pyrolysis and the biomass facility, we take that from literature. And for the revenue calculation, we have used Lazar's levelized cost of energy analysis. And when we do all this, it's around $100 per ton of CO2 captured and like $105 per CO2, which is per climate effect value, which is okay, better than most values that we see in the literature, but literature is all over the place in terms of that financial assessments. Just like any other project, any other system, any other technology that employs biochar as a CDR method, we have co-benefits too. That's all known things. I mean, biochar applications known to enhance soil and carbon levels, support plant growth, especially in tropical regions where the soils are weathered, acidic, and contains low nutrients. These improvements are due to not only like the nutrient content of because biochar doesn't have a nutrient content that much. I'm talking about biochar composted into a fertilizer. But biochar itself does the soil aggregation, increase water retention, etc., etc. And as a result of that improved crop yields, we can just cut off, and not cut off, but reduce the use or reliance on chemical fertilizers. But that heavily depends on the type of biochar. Our biochar produced in that plant may not be suitable for this, and of course, the composting process too. You have to compost it with soil and etc. to make it like nutrient rich, and that requires a lot of optimization and a lot of experiment. Along this, it's not just only sequester carbons. It can just reduce CO2 emissions in especially low soil organic carbon soils. But in soils that have high levels of soil organic carbon, the application of biochar might increase the CO2 emissions because of the mineralization of biochar's labile fraction, that is not stable fraction. It can catalyze the decomposition of soil organic matter, or it can again have a stimulated priming effect and just increase the decomposition of everything in the soil. Beyond that, beyond CO2, it can reduce NTO and CH4 emissions, nitrous oxide and methane emissions. There is there are several mechanisms. I'm not going to talk about the mechanisms to soil aeration and inhibiting the activity of the nitrifying and ammonium oxidizing bacteria. But these are just some of the studies. They're not like true. So many things, so many other like experiments needs to be done on this to be very sure about its exact effects on soils. But this all tells us that we need to carefully select the soil that we will apply or biochar. It can be beneficial, but it can also everything just goes south, and we can maybe just increase this CO2 emissions or other methane or N2O emissions too. This depends on the soil and the interactions between soil and the biochar. This is again a biomass-based CDR strategy. So its main drawback is the land, and it's actually what I call the problem with the scarcity of the biomass. But it's a good thing that we have used Miscanthus in our project because it's first of all it's a very resilient and drought-related energy crop. Thus, it can grow like everywhere where generic agricultural activities fail, where you can not just produce like food, you can just produce miscanthus. So it production of that crop does not have to compete with the food production, and it can be using marginal lands so that we can just decrease the land use change. That is one of the main factors that affect the potential of that potential of any actually biomass-based large industrial CDR solutions. For this is true for bags too. You need land and you want to reduce that land use change as much as possible. And for either case, for marginal use or not, we need like 31,000 hectares of land, and that based on 30 tons of biomass per hectare, that is a very, very optimistic assumption. For facility, we don't have like many much land needed. For biochar application, we need like 49,000 hectares of land, but I mean, you can apply biochar to anywhere. It doesn't constitute any land use change, so it's actually excluded from this calculation of land use, land requirement, but nevertheless, we have calculated and presented it here. To sum up, it's biochar plus CCS is a long-term measurable and verifiable CO2 removal technology. It facilitates self-sustainable pyrolysis and very efficient energy and byproduct utilization. It has a high net carbon removal and a good cost estimates, at least for now. And depending on the soil where you apply your biochar and the type of biochar that you produce, it can be very beneficial in terms of the co-benefits. And if you could manage to grow miscanthus in a marginal land, if you can find that large of a marginalized land, the selection of miscanthus is actually boosts this technology much further when compared to like the power plants with the use of like trees or wood chips. Yeah, 25 minutes. Here's all my references. Thanks you guys for listening. I can just take any question right now.
Thank you very much, Ali. I mean, I know your work already because we're in the same project.
Yeah.
But so you got a question from Henry. Is the combustion of the bio oil and gas used to produce energy for industrial applications, or is that energy fully used for the CCS units?
No, we have net 100 megawatts of energy. CCS only takes like without the CCS, we could produce 115 megawatts. CCS takes a lot, but like 15% maybe.
Okay. And the other question was regarding the TRL. What would you assess is the TRL level of that system?
Yeah, that's probably 0 or 1. I mean, it's just the hypothetical scenario.
But
Maybe
but
you
but
could,
but
yeah.
if you say you have the current, I mean you have the individual technologies, what would you
I,
say? How tricky is it to combine them? How long would it take?
yeah, I mean, not very much actually. It depends on the market. It depends on the biochar market. If you could sell your biochar, it all comes down to money, unfortunately. But if you could just sell your biochar, uh, it makes because the system, when given the same amount of biomass input, this system produces less energy than uh, a BECCS power plant. So less revenue than BECCS power plant. But if you could just sell your biochar and if you make a revenue out of this, then it could be economically feasible. And actually, it doesn't change much in terms of CO2 capture when compared to BECCS. But you produce biochar too, and you can just benefit from its co-benefits or anything. Why we use biochar.
And because we heard it in the presentation before. So what's the, did you look at the effect or the impact of transport costs of the biomass on the overall system
Yeah.
performance? And do you have any um, limit where you say, okay, if I have to transport the biomass for, I don't know, 200 kilometers or 100, it becomes very inefficient or something like that?
Yeah, it depends. I mean, we can ship it. I mean, the plant is located in Europe. We choose like UK for the reference
Hmm.
location. You can ship it from United States or Canada, or you could in the ship because it's very less CO2 intensive. Or I don't have any threshold for this, but in the end, it doesn't make a lot of difference. It makes a majority of the emissions of the plant, but it's quite impossible to reach that level of CO2 emission that would like equalize with that CO2 reduction.
Yeah, I mean that's the benefit of a CCS
Yeah, it's yeah,
of a
quite
CCS
efficient.
unit. Yeah.
But
Okay.
it's costly, of course.
Yeah. Yeah. That's why we don't see them around yet.
Yes.
Definitely. Um, so thank you very much. I think we are a bit over time already.